Have you ever just stopped and listened to combat drone footage? You've got the deafening chainsaw-like roar of one platform, followed by the absolute dead silence of another. You aren't just hearing machines. You're hearing highly calculated engineering solutions dictated entirely by battlefield missions. In this explainer, we're going to explore how the harsh realities of modern warfare force engineers to make radical choices in propulsion.
Here is our roadmap for today. We'll start with how tactics dictate power choices. Then, we'll dive into the Shahed 136 for long-range attrition, the Orlan 10 for extreme endurance recon, the Lancet 3's electric strike capabilities, and finally, wrap up with next-gen hydrogen and heavy platforms. All right, part 1. Tactics dictate power choices.
Look, in aerospace engineering, there is no such thing as a perfect engine. There's only the right engine for the job. So why do modern drones sound so drastically different from one another? Why do some roar like a two-stroke lawnmower for miles, while others glide in completely silently, giving absolutely no acoustic warning before they hit? It all comes down to the uncompromising laws of physics.
Engineers face some brutal trade-offs here. Internal combustion engines, good old ICE, give you incredible energy density. You get massive range out of carbon-based fuels, but at the cost of painting a giant acoustic and thermal target on your back. Pure electric setups totally flip the script, giving you that coveted zero noise, zero heat stealth, but heavy lithium-ion batteries deeply limit your range. And hybrids, well, they try to thread the needle to balance efficiency with power demands, but they add a ton of mechanical complexity.
Moving to Section 2, the Shahed 136 and long-range attrition.
Get a load of this number, 150 liters. Out of the Shahed 136's roughly 200 kilogram takeoff weight, an incredible 150 to 160 liters of that is literally just fuel. It's basically a flying gas tank. This massive fuel fraction is exactly what allows it to achieve that staggering 2,500 kilometer operational range. It trades agility and stealth entirely for sheer brute force distance.
And that philosophy totally dictates its power plan. The drone uses a Matto MD550 engine, which is actually a reverse-engineered copy of a German Limbach L550E. It's a four-cylinder, two-stroke engine pushing out about 50 horsepower. They use cheap commercial parts, giving it that infamous loud moped acoustic signature. Because it's designed for one-way saturation attacks, the engine lifespan is super short, sometimes failing after just 4 to 5 hours of operation. But for a disposable marathon bomber, that is entirely by design.
Section 3. The Orlan 10 and Extreme Endurance Recon.
Now, to achieve extreme endurance, the Orlan 10 takes a wildly different approach to internal combustion. While the Shahed uses a two-stroke engine, the Orlan 10 utilizes a micro four-stroke engine, specifically models like the Saito FA62B. Yes, a four-stroke engine is mechanically more complex, but its exhaust process doesn't waste unburned fuel. The result? A massive 40% lower specific fuel consumption compared to a two-stroke. This drone sips gas like an ultra-efficient hybrid car, allowing it to stay airborne for 16 to 18 hours on a minuscule amount of fuel.
But here's the catch. Putting a thumping single-cylinder engine right next to sensitive cameras creates a massive vibration problem. The structural workaround is pretty brilliant. They isolate the optics in a gyro-stabilized pod using heavy rubber shock absorbers. Furthermore, because this drone doesn't use a runway, the engine crankcase and gearboxes are heavily reinforced to survive over 10 Gs of force during catapult launches, not to mention the violent physical impact of parachute landings. It is built incredibly tough for rugged field conditions.
All right, Section 4, Lancet 3, the electric assassin.
When total stealth is non-negotiable, the Lancet 3 completely abandons liquid fuel. It utilizes a pure electric drive, powered by a high-performance Czech Axi 5330 brushless motor and a LiPo battery. Sure, that limits its flight time to just about 40 minutes, but the tactical trade-off is immense. It acts as an invisible cloak. You get zero mechanical roaring and virtually zero thermal exhaust. Enemy radar and infrared systems have almost no time to react because the drone blends right into the background noise of the battlefield.
But do not let the word electric make you think it lacks power. This thing boasts a terminal dive speed of 300 kilometers per hour. When its onboard AI computer vision locks onto a target, it utilizes a unique double X-wing aerodynamic layout and that high-torque electric motor to perform a high-overload dead silent dive. It delivers devastating kinetic energy against armor or air defense systems before the enemy even knows it's there.
Finally, Section 5, Next-Gen Hydrogen and Heavy Platforms.
First, let's talk about heavy-lift electric multirotors, like the Mammoth FPV. Big multirotors like the Mammoth require absolutely massive spikes in power, what we call transient currents, during takeoff and heavy evasive maneuvers. Standard batteries would just melt or fail under this load. So engineers are integrating extreme high-power cells, like molacell batteries, which can handle up to 100 amps of pulse discharge and insane 50 to 80 C transient currents. This allows heavy drones like the Mammoth to carry huge payloads while maintaining the rapid response times of pure electric flight.
But what if you want the extreme endurance of gas combined with the total stealth of electric? Enter the hydrogen fuel cell. Lithium-ion batteries are heavy and have pretty low specific energy. Hydrogen PMFCs, proton exchange membrane fuel cells, offer a revolutionary alternative. They literally generate electricity on board to drive the electric motors. That means you get the silent, cold signature of a battery drone, but with a massive leap in efficiency.
A perfect example of this in action is the new hydrogen hybrid variant of the Skyton Raybird. To make this practical, engineers had to completely redesign the airframe to safely distribute the space and weight of pressurized hydrogen tanks. The result? A drone that flies for 12 hours in complete electric stealth, operates flawlessly in extreme climates from -35 to +55 degrees Celsius, and features quick-swap hydrogen cartridges that make field logistics as easy as swapping out a battery. It's really the best of both worlds.
We've seen how tactical needs dictate every single nut, bolt, and battery cell in these machines. From the loud, brute force marathon of the Shahed 136, to the silent surgical strike of the Lancet 3, and right up to the cutting-edge hydrogen endurance of the Raybird. As hybrid and electric propulsion technologies become lighter, cheaper, and vastly more powerful, how will this relentless cycle of engineering innovation fundamentally reshape the battlefields of tomorrow? Thanks for joining me on this explainer, and keep your eyes on the skies.